Emeritus, and unfortunately he's not here today, but it's mostly his work. And what we wanted to do with Eric was to try to identify or to find general patterns in the way that plates diversify. It's not only a question, so it's something that evolutionary biologists have been, a question that has been asked for a long time, and something that we are trying to do is to identify from phylogenetic trees if we can find general patterns in the tempo and mode of diversification across groups and so on. So there's several reasons why we do that. Obvious reasons are because if we want to try to understand how biodiversity is distributed on Earth, across the tree of life, to test different evolutionary hypotheses about diversification and so on. And here I just put one example of a question that has been asked a lot, is how widespread are evolutionary radiations. That's just one example of how we use diversification models, and we're asking basically how often do we see in molecular phylogeny a signal of speciation rates that decline through time, and we might interpret that as a signal of an evolutionary radiation. So that's the approach that we have to tackle these questions is to develop different models of diversification and then find ways to fit these models to molecular phylogenies. And I'm not going to go too much into the details of the different models that we use to do that. There's a whole bunch, and it's not the purpose of the talk today. But I go straight to the conclusion, is that by applying these different models of diversification that we have to a whole bunch of molecular phylogenies, people haven't really come up with a real consensus on general trends, general patterns in molecular phylogenies and in the ways that plates diversify. So here, for example, we have three meta-analyses of phylogenies, so where people have used this approach of fitting diversification models to a whole bunch of molecular phylogenies. The first one, by Denisi et al. In Nature in 2010, came up with a conclusion that most of phylogenies were supporting a model where the rates of speciation and extinction are constant through time, which we interpreted as a support for the red hypothesis anyway. But so that was the conclusion here, is that most phylogeny supported model with constant rates of speciation and extinction. Myself with colleagues wrote also a paper looking for patterns in the tempo of diversification through time, and from this time a lot of phylogenies supporting models where rates vary through time, and in particular where speciation rates decline through time. And this year there's another paper from people doing the Tree of Life projects with Blair Edges and so on, who came again with the conclusion that most trees were supporting constant rates of speciation and extinction. So basically, there's not really a consensus in the field on that. Again, I won't delve too much into the details of why we don't come to a consensus, but basically this approach of modeling is great, and we continue to do that in the group, and the field continues to do that. But with this approach, we have a limited number of models of diversification that we compare phylogenies to. There are different models that produce more or less the same likelihood support and so on. So there are issues. So what I'm going to present today is something that tries to do things a little bit differently in a model-free approach. So trying to characterize maybe the different ways that there are to make diversification in a model-free approach. So first I will present this approach, and then I will have an application that's a work in progress across animal phylogenies. Okay, so what this approach is an approach that's taking some ideas from graph theory, and so basically representing phylogenies as a graph, which is a natural way to represent it. And we know that from graph theory there's been a lot of work done on how to compare graphs, how to measure their similarities, how distant they are, how to cluster graphs, and so on. And one powerful way to do that is to construct from a graph. It's what's called a graph Laplacian, and it's this matrix here, which on the diagonal has the degree of the different nodes. So here each cell in the matrix represents one node in the phylogeny. There are numbers here from 1 to 7. The diagonal here is the degree, so the number of nodes that each node is connected to, and the elements here on the diagonal are made of the weights, which are basically the distance between nodes. And we know that if we summarize the information in the phylogeny by this matrix, and we use the eigenvectors of this matrix, and there's a lot of properties from graph theory that we can use. And in particular, something that we know is that if we look at the resulting distribution of eigenvalues, so here it's this is obtained by smoothing basically the suite of eigenvalues that we find by a kernel. This distribution summarizes more or less all the information that's available in a phylogeny. So we're not losing any information. We can reconstruct the phylogeny from this curve here, and so it's saying that compared to other summary statistics that might have been used in the field, this is a pretty complete way to represent quite fully the phylogeny. So now what we can do with that, because we have this easy way to represent this more complex object, is we have, okay, I went ahead a little bit here. So first, what I wanted to do is to show that basically this distribution of eigenvalues with spectral density represent main properties or reflect main properties of our trees that we're usually interested in. So here we see like the principal eigenvalue, that would be like the highest value here. It gives an idea of total phylogenetic diversity, so so a combination of species richness and phylogenetic branch length. The skewness of the distribution gives an idea about whether the tree is steepy or stamy. That's something that we'll be interested in a lot in the field also. Peak height gives an idea of the imbalance of the phylogeny, and the modalities, the number of modes we might see in the phylogeny, gives an idea of how different modes, like different phylogenetic patterns there are in the tree. So now that we have this nice way to summarize the information presented in a phylogeny, we can use classical measures of distance on distribution to measure the distance between two phylogenies. So here, for example, that would be the Jensen-Shannon distance. It's a classical measure that we can use to measure distance between distributions. And if we can do that, then we can use same thing like classical clustering algorithm to try to cluster phylogenies into several distinct groups, which might give us an idea of how many different distinct ways there are basically to diversify and how frequently we see that in nature. So first what we did is a proof of principle. So if we come up with this way to cluster phylogenies one with the other, something that we might want to happen is that if we simulate phylogenies with different classical models of diversification, that we can recover, we can recluster back these phylogenies in these different clusters. So that's what Eric did here, is simulated phylogenies with 6 classical models of diversification, and then apply the clustering approach. And what we see is that the approach is able to recover the 6 different ways in which we simulated the phylogeny. So it's a proof of principle by doing that we can recover main modes of diversification. Okay, so now we can apply that to empirical phylogenies. Again, this is work in progress. So what we have so far is first we've implemented this approach in a package that is also now implementing the main diversification models that we are building in the lab. So in case you're interested in fitting models that have been developed previously in the group, it's in this package, and in particular this new method is there also. And so now an application. So what we have so far is phylogenies that we have taken from classical phylogenies available in the literature. So phylogenies at the family level for mammals, birds, squamates, amphibians, fish, and some vertebrate phylogenies also. And we have applied the approach, and what we see is that there are 5 main, so the phylogenies clusters in 5 main different groupings. Here they are, so and here you can see more or less like the shape of the phylogeny that this clustering might represent. So there's 5 distinct ways to make diversification that cluster across these phylogenies. So now what we can do is try to see how they are represented across the different groups of animals that we've been looking at here, and we see that there's a big bias here because there's few phylogenies in this group and this group, but when we have a good representation of the groups, these different ways to diversify are present in more or less the same frequency across different groups. So if we look at how these different phylogenies, so here we have the empirical phylogenies clustered and on an ordination diagram according to the properties of their spectral densities. And so we see that the groups are distinct one from the other depending on properties of spectral density, so peak height, principal eigenvalues, the skewness. And we might see things that, like some part of this phylogenetic space that are not really a field. So there's like part of the way that phylogenies we could see that we don't really see in nature, and that's one way that we're starting to try to understand if there are constraints in the way to diversify that explain that we don't have this type of phylogeny here, or trade-offs in the way to diversify. So yeah, that's about what I had to say. So basically, we developed this new approach to characterize, compare, and cluster phylogenies. That's kind of a little bit ahead. We're still working on that, but if we apply that to empirical phylogenies, it seems that there's five main ways, five main different types of phylogenies that we see in nature. And so what we're trying to do now is to go back to the models and see these different types of ways to diversify. Can we characterize more in terms of, in terms of the classical models of diversification that we've been using? We're trying to see if these different ways to diversify are usually conserved, so is there a phylogenetic signal in which cluster the phylogenies fall into, and what I was talking a little bit about on the former slide, are there constraints and trade-offs in the way that things diversify. So with this, I want to really thank Eric, who was really